Okay, the second talk in this session is fully dynamic maximal matching and constant update time by Shai Solomon.
Thank you. I want to start with the basics, some definitions. Okay, so a matching is just a set of vertex disjoint edges, like these blue edges that you see. And we'll color those edges blue and the unmatched edges red throughout these slides. And we have two types of vertices, a free vertex like this one that is not adjacent to any of the matched edges, and a matched vertex like this one that is adjacent to a single edge of the matching. And we're going to consider undirected and unweighted graphs with n vertices and m edges. The most basic question in this context is to compute a maximum matching, maximum cardinality matching. In this example, you can see that the size of the maximum matching is 2, and you can always compute such a matching using a quite sophisticated algorithm that takes an m square root n time. That's true in any graph, and it's much simpler to get a maximal matching. That's it. It's not necessarily of maximal size, it is just inclusion-wise maximal. And this means that we just want to have that for every free vertex, all its neighbors are matched. For example, here you can take the middle edge, and that's already a maximal matching. And you can see that the size is a true approximation to the maximum, and that's always true. And this gives us a way to get a true approximation using a simple linear time algorithm. And we are interested in a dynamic setting where we have n fixed vertices, but the edges come and go. And following every edge update, we are considering the maximal matching problem, not the maximum. Following any edge update, we want the algorithm to update the matching as fast as possible. So for example, the first edge comes, and the algorithm should match the two endpoints. Second edge comes. So this should not be matched. And so we continue this process. And let's see, this matched edge gets deleted. The algorithm, something is wrong with the colors. So let's skip this example. And what we want to do is to get a small update time as possible. And we're going to focus today on the amortized bound. So the holy grail is to get a constant cost. And this means that if we have t edge updates in total, then we want the total runtime of the algorithm to be linear in t. And that's quite rare, actually. If you're looking in the area and you're considering general graphs, then usually you'll get a super constant amortized cost. Let's start with a very naive algorithm that will give us an order n update time. Following an edge insertion, we just check if the two endpoints are free. And if this is the case, we add the edge to the matching. And if this is not the case, then we don't need to do anything. So that's a constant time operation. If we delete an unmatched edge, then again, it's a constant time operation. Don't have to do anything special, but the only interesting case is when we delete a matched edge, and then the two endpoints become free, and we need to make sure that they don't have a free neighbor. So we just naively scan the neighbors, and if we find a free neighbor for u, we are going to match them, and the same goes for v. So the cost here, naively, is the sum of the degrees of the two endpoints up to some constant. But that's order n in general. And somewhat surprisingly, this has been the state of the art for quite some time. And currently, the state of the art is with the joint work with Neyman, where we get square root m update time. So for deterministic algorithm, that's the best that we currently know. But if one allows randomization, then there is a result by Boswana, Gupta, and Sen. They give a randomized algorithm with an expected amortized cost of log n. And in this work, we build on their framework and manage to, okay, so we give a different algorithm that has the constant amortized cost that we wanted. And I want to emphasize that we are following the oblivious adversarial model. That's a standard model in the area, and it has been used by Baswana et al. As well. And in this model, the adversary is the one adding and deleting the edges, and it may know how the algorithm works, but it doesn't know the random bits that are being used, and in particular, it doesn't know how the matching that we maintain looks like. So we have a few applications. I'll mention two of them. First, we get the two approximation to the maximum matching. You can compare this to the previous results. And perhaps more interestingly, we also get the two approximation to the minimum vertex cover. And there, it's essentially the best you can hope for under the unique games conjecture. You cannot get better than the two approximation in polynomial time. Okay, so let's get started with some details. And I want to recap the naive algorithm that we saw, which following a deletion of a matched edge, we just scan the neighbors of the two endpoints. Okay, we're going to focus on vertex V today. So the naive thing is to match to an arbitrary free neighbor if exists. Let's do something differently. Let's choose uniformly at random some neighbor. Let's say W2 was chosen, and match V with that neighbor. We have the degree of V options. Each of them will be chosen with equal probability. And since the adversary is oblivious to this choice, it will have to make many deletions among these edges before hitting on this particular edge that we chose. For each miss that the adversary makes, we gain money because we can update the matching very fast. So in the amortized sense, we get money. And the exact amount that we get, meaning the expected number of edges that the adversary will delete before hitting on this one, is quite large. It's roughly half of the degree of V. So now we can calculate the expected amortized cost of handling this edge deletion in the future. It's the ratio between the actual cost, which naively is just the sum of the degrees of the two endpoints. But now we are dividing this by the money that we got, the degree of V over 2. And if it happens that the mate of V that we chose is of low degree, we are good. The cost will be constant. But in general, we might get here an order n amortized cost. Questions? Okay, so what we are going to do is focus on a subset of the neighbors. We're going to sample from fewer neighbors, not all of them. And let's define for every matched edge E a certain potential value, phi of E. And it simply states among how many edges did we sample this edge. If V is the vertex initiating this match, then obviously the potential of the edge will be bounded by the degree of V. But sometimes, depending on how we do this sampling, the potential might be much smaller than the degree of V. And so we have to update this expression that we have, because the money that we now get from the adversary might be much smaller. It depends on the potential of the edge. It's the potential of the edge over 2 in expectation. And the challenge that we are going to face is how can we handle this edge deletion in cost that is linear in the money that we have, the potential of the deleted edge. That's what we are going to try and do. And okay, so we're going to do that using a potential-based sampling. What do I mean? Now we have, for every matched edge, we have a certain potential value. And we're going to define a potential value for the matched vertices. Simply, the two endpoints of a matched edge will have the same value as the edge. Okay, so phi of v is just phi of the corresponding edge. It's a positive integer. It's bounded by the maximum degree in the graph. And that's the value that we'll have for every vertex in the graph. And for free vertices, we define the potential value as 0. So there is a separation between free vertices and matched vertices. So, and in this illustration, you see a partition of the vertices into the n possible level, n possible potential values. All the free vertices have value 0. The matched vertices have higher values. And if you consider this edge, for example, it has a potential value of 2. This means that we sampled it from 2 options. And it also means that the two endpoints will have the same value of 2. Any questions about these definitions? So now that hopefully we understand these definitions, we can explain how exactly a mate is chosen for vertex V. And the rule is simple. We just sample a vertex uniformly at random from this set, n 1/2 V, which contains all the neighbors with potential at most half of the potential of V. So we want to go down by some constant factor when choosing a mate for V. For example, yeah. So if, yeah, good question. We'll get to it, hopefully. Let's see an example. This edge has potential 2, and it's deleted from the graph. Now, let's focus on vertex V. We need to find a mate for it. We're going to sample a neighbor, sample a mate for V from this set, n 1/2 of V. Now, in this example, V has a potential of 2, so we are going to restrict the attention to neighbors with potential value of 1 or less. There are 2 options in this example. We're going to choose one of them with probability 1/2. Let's say that we chose X. So X is the new mate of V. This new edge has a potential value of 2 because we had 2 options. And there's only one problem. We now have 2 matched edges adjacent to this guy. So we have to destroy some matched edge for this to be a valid matching. And this is exactly why we are going to restrict the attention to neighbors of lower potential, significantly lower potential, because we are losing now some potential, and we need to compensate for this. So how can we do that? By creating a new matched edge with significantly higher potential. That's the intuition, at least. And to your question, if I don't have any vertex here, then I also don't have any free neighbor. And we can use that. So in particular, let's see what happened. Vertex 6 had a potential value of 1. Now it's going to increase to value 2. And what I want to emphasize is that these values change dynamically. And the challenge is to maintain this set n 1/2 of V dynamically. But actually, we don't know how to do that. It will take time that is much larger than the time that we can afford to spend. So we don't have this set. What we can try and maintain is a superset that I denote by n of V. And this set contains all the neighbors of V with potential bounded by that of V. Okay, so possibly it's much larger than what we want to maintain, but we'll have to make do with this bigger set. And so again, I want to emphasize what I just mentioned. Both these sets contain all the free neighbors of V. Why is that? Because the free neighbors have potential value 0. So this is by definition true. Let's use this observation. Okay, so let's see how the algorithm will handle a deletion of a matched edge. we want to do that in time that is very fast, right? Time that is linear in the potential of the deleted edge. We are focusing on vertex V. And there are two cases. The first case is that the size of the set that we know how to maintain, just to remind you, the set of all neighbors of V with potential value bounded by that of V. So if the size of this set is small, smaller than twice the potential of the deleted edge or the potential of V, it's the same thing, then we have a lot of money. We're going to handle V deterministically simply by scanning the entire set. And we're going to try and find a free neighbor there, W, and if we happen to find such a neighbor, we just match them together and set the potential of the new matched edge to 1 because it was sampled from a single option. It's a deterministic choice here. So the potential here is now set to 1. We are not going to gain much from this edge. But maybe we didn't find any free vertex in that set, but then by the observation that I try to emphasize, V does not have any free neighbor. So we can leave V free and its potential is now 0. Actually, this is the easy part. What's difficult is to understand what's going on when there are many vertices in this set. We cannot scan all of them. It's much larger than the money that we have. It's possibly much larger than the money that we have. And what we would like to do is to sample a mate from this set that we don't know how to maintain. So ideally, we'll just take a random vertex from this set. We don't have this set. We have a possibly much larger set. N1, instead of N1 half of V, we have N of V. So how can we do this sampling in time that is linear in the potential? That's the thing that we want to resolve. And the idea is somewhat naive. We're just going to increase the potential. If we don't have enough money, increase the potential. It's actually the only thing I could think of. So, and it's going to work because let's do this potential increase by multiples of 2. Okay, so we are starting with a very large set, NV, with respect to the money that we have. We are going to increase this potential starting from 2 times the potential of V, 4 times, 8 times, 16 times, and so on. And as we do this increase, we need to update the set N of V because more and more neighbors of V must be added to that set. And at some point, we're going to stop. Whenever the size of this set is smaller than twice the new potential phi. Why am I sure that we are going to stop? Because the left-hand side of this test is bounded by the maximum degree, and the right-hand side will exceed it whenever the new value that we choose is large enough. So at some point, we'll stop, and there is a caveat here. Updating this set N of V as we increase the potential is highly non-trivial. I'm completely ignoring this now because I want to make an observation that is probably the key to the correctness of this algorithm. We did stop eventually, and when we stopped, by definition, we have this inequality. The size of the set, the size of the bigger set, NV, is bounded by, let's say, order of phi. But we didn't stop earlier than that. We didn't stop at the previous. We didn't stop at the previous attempt at potential value phi over 2. So at that stage, this test failed. What do we get from this failure? The size. I mean, if you look at the set N of V at the previous potential value, is exactly the set N1 half of V right now. And since this test failed, we have here an inequality in the other direction. We have actually this thing. We get a lower bound on the size of the set that we want to maintain. It's a large set relatively to the bigger set, N of V. So we are just going to go over the bigger set, N of V. Yeah, combining these two inequalities, you get that this subset is at least half the superset. So this gives us the option to just go over all the vertices in the superset and construct the subset n1 half of it that we didn't know how to maintain. We are doing it now from scratch. And the entire cost is just order of the new potential value. And now that we have this new subset, we are sampling a random mate from it. And there are many options. There are many options to choose from. So we are sampling over many vertices. This means that the new match stage that we are constructing has a high potential. It's indeed phi as we wanted it to be. And this means that the adversary will have to make many misses, at least phi over 2 misses, before it hits the edge that we just created in the matching. So this should give us the omega of phi tokens that we wanted. That's the money that we need to implement the entire procedure, and we are basically done. So that's I think the key idea, or at least one among two key ideas of the algorithm. And I want to conclude. We gave a constant amortized cost for this problem, and that's quite rare bound in the area of dynamic graph algorithms. And using existing ideas and by developing a few new ideas, we got a new technique, and it would be interesting to apply to other problems in the area. And there are many open questions. I just mentioned it would be interesting to get a worst case bound to this problem, or a deterministic algorithm. And of course, attacking this from the lower bound side would be interesting too. So thanks. Mm-hmm. That's okay. So the fear is that we are charging. So there are two cases. Either we charge the past, which is when the size of the set is small, then we can charge the past. If the size of the set is large and we are starting to increase the potential, we are actually charging the future, like you said. But I'm assuming that we are starting from an empty graph. If we don't start from an empty graph, everything fails. If we're starting from an empty graph, you can assume that the graph, that the sequence ends at an empty graph. It's going to increase the number of updates by a factor of 2 at most. So, but that's a good point. I should have emphasized it. Actually, let me mention that I don't know how to communicate 2 steps away. If I did, I would get here a better than 2 approximation. Yeah, so yeah, we are communicating it 1 step away. And just one thing that I couldn't emphasize because I didn't have enough time for that. It's unclear how to communicate the change of the potential to all the neighbors. This is actually a central point in the algorithm that requires modifying this simple potential increase procedure that I described. So propagating these changes in the potential values is quite challenging, and even 1 step away is non-trivial.